Of course, in my previous video, I introduced you to exponential family of distribution. And I remember I walk you through an example of one parameter family. So what I'm going to do this time around is to walk you through a multi-parameter family. Of course, if you take a look at the distribution, probability distributions we have, an example of a multi-parameter family is a normal distribution. Okay, a normal distribution has two parameters, okay, mean and standard deviation. And of course, beta distribution, talk about beta distribution of the first kind, also have two parameters. Okay, so what I actually want to talk about now, I'm going to share my screen and we want to work on, we actually want to work on, example, a beta distribution. Okay, I got Excel follows beta distribution of a first kind. And with the parameter alpha beta, okay, we got two parameters here. Okay, so what I'm talking about the other times, like our theta, we having alpha and beta, okay, as a parameter. Okay, so the f of s, given this alpha beta is actually x raised to power alpha minus 1 minus s raised to power beta minus 1, okay, divided by, so this is going to be gamma alpha plus beta divided by gamma alpha, gamma beta, okay. And of course, if you take a look at the distribution, the support of x is 0, 1, and alpha is positive and beta is positive as well. So, what we actually want to figure out is we don't, the two parameters are unknown. Alpha unknown, beta unknown. Of course, we know that alpha is greater than 0, beta greater than 0. But all what we want to do is to see whether we'll be able to, establish the fact that this is an exponential family. Okay, and if that is exponential family, we'll be able to obtain the joint, sufficient statistic for the two parameters. Okay, so now I'm gonna walk you through how to do that. Okay, so of course, if I want to write this guy now, don't forget I said it's actually gonna be ESP. Okay, so the ESP into the lean, okay, of S given alpha beta. Okay, now what I'm gonna do now, so I'm gonna do ESP, okay, into lean, and I'm actually gonna put the distribution now. That is exactly what I'm doing, okay, and gamma dot divided by gamma alpha, gamma beta. Okay, take a look at what I have now. Okay, so I've been able to, write this in terms of exponential lean of the probability distribution given. Okay, now, of course, this distribution is very, very important in statistics because um, the random variable s lie between 0 and 1. We can actually use to figure out the probability that customers, certain percentage of customers will prefer your products. I want to believe 100% of customers cannot prefer your product. Okay, so we expect that to be in the region of 0, 1. Okay, so this is a model for proportions. The random variable here is actually proportion. Okay, you may want to find what is the probability that approval rating of the president of a country is actually greater than 50%. The random variable here, the random variable will follow beta distribution. Okay, now all what we just need to do now, I need a space, I need a room. I'm actually going to simplify that. So this guy is going to be equal. So I'm actually having lane of all of that. So I'm actually going to have ES of P. Okay, I'm going to have lane S, lane of this guy here. Okay, then I'm going to have plus lane of 1 minus s raised to power beta minus 1, as you can see. Okay, that is more or less like a product that I'm actually going to have the lane into alpha plus beta now divided by gamma alpha gamma beta. Okay, that is exactly what I'm going to have. So I think I'm actually using the knowledge of mathematics now. Okay, in statistical theory, we actually require mathematical knowledge. Okay, so if I want to rewrite this now, I'm actually going to do alpha minus 1 ln of s plus beta minus 1, okay, plus ln into gamma alpha plus beta over gamma alpha gamma beta. Okay, so when you take a look at this now, I'm actually going to call this two-dimensional exponential family. Okay, it's a two-dimensional exponential family from what I'm actually seeing now. When you take a look at give me 1 second. Oh, okay, I think something is missing here. So plus beta minus 1 ln 1 minus x. Okay, as you can see here. Okay, so that alpha minus 1, I'm actually going to call it c of theta, where theta equal to alpha. Okay, and when you take a look at that guy now, is actually alpha minus 1, right? Okay, and when you take a look at this guy, I'm actually going to call that guy T1 of x. Okay, T1 of x. And when you take a look at this guy, okay, I'm actually going to call it C2, where my theta equal to beta. And when you take a look at that guy, it's actually going to be T2 of x. Okay, we actually, you can see that right now. And of course, I'm actually, this guy is just going to be a function of theta. Okay, a function of theta, which is a function of alpha and beta. Okay, so when you take a look at this is a multi-dimensional. This is like a two-dimensional exponential family, because two unknown parameters are involved. Then we are also expected to have a joint sufficient statistic. Okay, so the sufficient statistic we now be 2. So I'm actually going to say T1 comma T2. And what is my T1 and what is my T2? Okay, my T1, okay, my T1 now, okay, is actually ln of x, okay, and my T2 is ln into 1 minus x. Okay, so the sufficient statistic is going to be summation T1, which is going to be summation ln s, and the other one summation T2, which is going to be summation ln into 1 minus x. Okay, so those are my sufficient statistic. Okay, so that is how we do it.